My name is Sean Allen. I'm the VP of Engineering at Walloon Labs. We build a high-performance stateful stream processor, which is really designed to be able to allow you to go fast and not corrupt your data. So this is a topic near and dear to my heart. I'm also the member of the core team for a programming language called Pony, which is a programming language which is designed to allow you to write programs that go fast without corrupting your data. Again, something that's along the lines there. And I'm a very spoiled Boston sports fan who will be watching Game 7 of the Stanley Cup tonight. Because the power is out at the Marriott and I'm staying at the Marriott, if you're interested in watching the Stanley Cup, I think at this point I'm going to have YouTube TV and I'm going to be sitting in the lobby at 5. Feel free to come by and join me. Unless you're a Blues fan, then please do not come by and join me because I don't want to put up with you if the Bruins lose, not that that's going to happen. You can find me on Twitter in all of these places for various different things. If you follow my personal one, sorry, sometimes I tweet an awful lot. This talk really is about scaling, right? In particular, it's about scaling data handling applications. And really, in particular, it's about my reaction to one term, and that is stateless. I have a very conflicted relationship with this term. It generally gets used in a hand-wavy kind of way when people are talking about how you scale applications. That hand waves away a lot of problems. The number of people I've heard tell me it's like, oh, well, that's a solved problem. We'll just make everything stateless. And it often becomes a rhetorical device that really seems to be used in a lot of conversations to mean, you know what, you don't have to worry about this state, about this data. Just write the application thing that you're interested in and don't worry about the rest. And that's an incredibly seductive idea. I mean, I spent a lot of time as an application developer and you know, the state and the data handling parts of what we do, that's the really hard part of scaling. So to have somebody tell you that it's a solved problem and you don't have to worry about it, and we have these patterns which will allow you to do this without issue is a really nice thing. But you know, I'm going to talk today about how, at least for an awful lot of the patterns that we have data corruption that are built into those. I'm going to cover an awful lot of things today. So this is really an overview talk. We're not going to go deep enough into anything where you're going to be an expert in any of these things, but you should come away with it with an idea of things that you might want to learn more about and whatnot, right? This is today's topics, right? I'm going to cover, data corruption, concurrency, data races, shared values, atomic operations. If you don't know what all of those are, that's fine. We're going to touch on each of those. And again, because each of these is something you could do a 40-minute talk easily on each one of these, and I'm not going super deep into any of them. There's a GitHub repo, which you can go to, and I'll also put this up again at the end, which has an awful lot of additional resources where you can learn more about everything that's there. So before I get started, just a question I always like to know a little bit about the audience. How many people here have written single process programs where you concurrently access shared mutable state? All right, good, okay. Some of this might be clear to you. And how many people here consider themselves distributed systems experts? Nobody ever puts their hand up for that. Nobody. I really want to meet the person who's going to put their hand up for that. I really do. I want to have a long conversation with them. Anyway, there are a lot of generalizations that are going to be in this. If you know a lot about one of the particular topics that I'm going to cover, you could well actually me to death. Feel free to well actually me afterwards if you want to. And if it's something you don't know about, know that if you go out and tell people exactly what I told you, that it's not really going to be true and somebody's eventually going to well actually you. There's a lot of convenient lies that are in this talk. They're sort of broadly covering something which is fundamentally true, but often, I've simplified a lot of the details in order to make it so that we can cover really what we need to cover. And, I'm okay with that kind of lying. It's pretty much how we go about teaching stuff anyway. We teach you a simplified version, and you get more complex as you go along and you start to understand the topic. So For example, this is my first generalization and sort of lie, right? Is that our most popular architectures can be traced back to web applications. For me, this is a convenient lie for a number of reasons, in that, one, I started my career around the time when we first started building web applications, you know. There's a little thing going around Twitter right now about how you're old if you ever used like a SVN. You know, I started my career working with Sun OS in RCS, so that must make me ancient, and I'm going to keel over and die when this talk is over. But so with this is we can definitely trace like a lot of our modern architectures back through to web applications. And from how we built web applications, you could actually go back further, but this is a nice starting point for me. So if we were to create one of these nice diagrams that we often like to create as software engineers, you know, a web app would look something like this, right? We have this web application which is running in a process, and it's going to be talking back and forth with the database. Nothing particularly complicated. And in the end, most stuff that we have on the web could be simplified down to this if you really wanted to, right? And a bit more detailed on this. You know, we have a request which is going to come into an application, and then we go on to the database, and we come back to the application, then back out again as a response. Or, you know, we could break that down still further and talk about how the request is coming from a web browser, probably, maybe now, not necessarily. It could be through an API. And our application is probably a web server and some developer code, and et cetera. And in this case, you know, we have this back and forth between our application and our database, and you know, our simple web app is a distributed system. We're crossing from machines and processes. So a lot of people like to talk about how distributed systems are hard. I think that's untrue. I think they're really easy. If you like one of those Twitter people, you could take a picture of this, put it on there, please, without any context, and make a lot of people really angry at me. Make sure to put my name on it right there as well, right? And get a lot of really angry people, right? But, you know, I really think it is true. I mean, concurrency is the hard part of this. Oh, you going to take the picture? Hold on, no, please do. Yes, no, I want to cause trouble. Did you get the picture? Okay, good. All right, good. You can cause trouble. Excellent, yes. I mostly give talks so I can cause trouble. I didn't get a lot of sleep last night because the Marriott thing. I'm usually better about clamping down on my snark during talks if I'm rested, but this is more the me that grew up like singing in punk rock bands and everything, a bit more of that, a bit more of the snark. Anyway, hopefully that doesn't offend anybody. So concurrency, that's really the hard part of this right here. And, you know, I got a little bit of justification for that. Most of this talk is really the justification for that statement. So going back to this in our web app and web application, you know, I want to dig into what's actually happening between these two things. In particular, I want to look at the arrow that's on here, right? Whenever we make these diagrams for applications, we always put these big boxes, you know, of the different systems interacting with one another. And we put these little arrows in between them, and then we spend all of our time talking about, like, the big boxes, like those are the important things. And sorry, the big boxes aren't really all that interesting. Like, what we really need is we need this thing where, like, yay, the arrow is our star, right? This is what we really should be talking about, is the interaction between different things in our system, right? This, like, I don't know, if I saw that as a diagram, I'd probably spend a lot more time thinking about that arrow. So today we're going to talk about that arrow. And we're going to talk about that arrow with a really simplified example application, which, depending on how old you are, is probably going to sound really foolish. But if you were actually old enough to be one of those people who used RCS and Sun OS, you'll recognize that people actually wrote early web applications that did exactly this. So we're going to talk about our pages served counter application, right? And the idea of this application is that every time we come to a web page, it's going to tell us how many pages on our website have already been served, right? This was a really big deal in the early days of the web. We put up little things on there so you could know how popular a website was. Like if it said, like, you know, hey, you know, this website's had 1,000 pages that it served, you knew that, like, this was a serious big time operation there where, like, you know, it's like, whoa, these people probably ended up as, like, cool site of the day on Yahoo. Yeah. One person probably knows what that is. Anyway, I'm really kind of stuck on that I'm old because of RCS thing. So The pages served counter. What is this application, right? In the end, this application is one where we read the current value from the database, that is the number of pages that we've already served, right? And we're going to add 1 to it in order to update it. Makes sense? We're serving a new page now. We're going to write that value back to the database so that when somebody else comes along, right, they'll get the correct value for theirs as well. And we're going to return this new value where we added 1 to it to the user to show, hey, this was page 57, that's been displayed on the site. So let's take a look at that. How many people can spot the data corruption that exists in our application that's right there? All right, you people are not going to, you're going to be bored for the rest of the talk. Just whip out the laptops and everything else, right? For everybody else, you pay more attention, all right? Okay, so again, this is what we have going on here. This really simple application right here. There is data corruption in this. We're not going to get correct results. It's not, because computers, they're hard apparently. So, like I said before, concurrency is really the hard part. When we add concurrency to this, it's going to be trouble, right? So maybe let's put this side by side. We now have 2 requests that are happening. They're executing this application at the same time. If you didn't put your hand up before for spotting the corruption, when you look at them side by side, do you see the corruption now? Hand up if you do. All right, I think we got everybody, in which case it's going to be really boring for a couple minutes while I explain it, but if not. So the big question here is, what is the final value of this if we start from the very first time this website runs? Is it 1? Is it 2? Damn. We really don't know. We have these 2 requests that came in at the same time, and interesting things can happen, right? Because what we're doing here is we have these things where we have these 4 operations for each one of these requests, and they can be interleaved in any fashion where we don't know what's going to execute at one point in time when we're doing this concurrently, right? So, let's say that we have this as a series of interleavings where everything in blue there is our request A, and everything in orange is our request B, right? So if we do this where it's just we do 1 step from request A and 1 step from request B, you can see when we get to the end here, both of these people are going to see 1 for a value that was on the page. But we know that we just did 2 requests, so that should be 2, right? But it's just 1 here, right? But if we use this interleaving where, for whatever reason, every step from request A gets executed first, and then every step from request B, which was started at the same time, we're going to end up with 2, which is the value that we would have expected, right? And, we have still other interleavings, like here's another one. It's slightly different. We're mixing them in together, and we still end up with the 2 that we know that we should be getting. And because the important part of that one here, this other one that we're showing, is that this write new value to the database step from request A is happening before the read current value from the database, right, in step B. And if those things don't happen in that order, then we're going to end up with an incorrect data value, and we've corrupted our data, right? The term for this, if you're not familiar with it, is a data race. This can occur not just in distributed systems. If you've ever written multi-threaded programs where you're accessing data at the same time, you have the exact same thing that happens. It's especially fun where you have CPUs now, which will do lots of stuff where they'll actually reorder their instructions for you on it, where you can end up with all of these, right? So the recipe for a database with this is that we need to have a shared value, right? There needs to be some state, some mutable state that's going to change that we're sharing. We need to have concurrency. There needs to be at least 2 things that are trying to change the value for that at one time. If there's only 1, then it's not really a problem. So we got to have those. We got to have the writer there, and we need to have non-atomic operations. Just out of curiosity, I know how much time to spend on this. How many people really feel like they know what an atomic operation is there? All right, we'll spend a moderate amount of time. So, in our problem here, though, we have our database as a shared value, right? It is a big, giant blob of mutable state. It happens to be on the other side of maybe a network connection, maybe a Unix domain socket, who knows, but we have it there. we have concurrency in the form of these two requests, right? And we got a lot of writing that's going on here as part of this. And the incrementing that we're doing isn't atomic, really. The way that we're adding to this is not atomic. And an operation is atomic. Like, atomic gets used in a lot of different contexts and a lot of within programming. I'm taking here one which is sort of a bastardized version of what you probably hear in the world of databases. And I'm going to say that an operation is atomic if it's isolated from other operations that are happening at the same time, right? And databases tend to provide something like this. So if we go back to our interleavings here, right, where we have this from one where we ended up with an incorrect value, right? And if we were to take these 3 steps, which were part of our algorithm, which a decent number of us who were in the room when we first looked at it said that seemed reasonable. These 3 operations right here are the 3 things that are part of incrementing as far as we're concerned, right? We're getting the value from its location in the database. We're updating it, and then we're writing the value back so that other folks will see it, right? And for this to be atomic, what we need is for this not to be able to have interleavings from some other requests happen within it. And we can see we have the interleavings here, right? So if we were able to turn this into something where it just becomes increment current value, where it is an atomic operation, right? Then we don't have this problem anymore. We can sit here and interleave this new algorithm in a fashion where we're going to increment current value, read new value, and the return value to user, we're always going to end up with 2. It really doesn't matter like what order that we put these in. We're going to get 2, and we're going to get the correct value there from that. And big reason for that is that we've eliminated our recipe for a data race in this particular case. We've addressed that, right? This actually can get even worse if we add more concurrency to it here. We only talked about it in terms of 2 requests that were coming in. We had that. So let's wind back and let's pretend like we're not doing the atomic operation for the incrementing. We're going to go back and we're going to go back to our original algorithm, right? And we're going to have 3 requests now. And what we have here is, imagine that the line going across there is its time. So these things, this is how they're ordered in particular bits of time, right? And we're going to start here by request A and request C arrive at the same time, and they're both going to read the value 0 from the database for our algorithm, right? And then at a little bit further along, based on how the operating system is scheduling whatever is happening, request A is going to update that value by adding 1 to it, right? And then we're going to write that value back to the database, right? So that's now 1, and that's all good. All right, database value is 1. And request B now is going to read the current value out of the database. So we get 1 there. It increments it to 2. And it writes that value back where it's 3, right? Sorry, where it's 2. And that's all well and good. This was one of the interleavings that we had before that was good. Everything for request A happened before everything for request B, so we end up with the value we want. We got 2. The problem is that we have request C down here, which is really slow for some reason, you know, computers, Linux scheduler, completely fair scheduler, and it's been moving along slower. So while all those others were going, it started at the beginning by reading 0 from the database, and then it finally eventually adds 1 to it, so that when it writes that value back to the database, you know, we've gone from 2 back to 1, right? Which is definitely not what we wanted. We wanted 3, right? This is actually kind of even worse than the corruption we had before, where it was, oops, you know, we never saw the correct value and then blew the correct value out of the water. We just completely wrote this over. And, you know, this is literally how I spent like 2 years of my life at one company, was basically tracking down corruption of customers' data that basically came down to this exact same type of problem. If you've ever been involved with database stuff at all, this probably just the thought of it, like, just makes your skin crawl a little. What this is called last write wins, right? More snarky quotes if you want to put them on Twitter coming up. You certainly can. Last right wins is basically, it means, some rights lose, right? Not all of them are going to win. Some of them are going to lose. It's from my friends Sean and Russell. They worked at Basho, a database company, run that. I'm a bit snarkier. I really like to say that last right wins is a fancy name for let's corrupt some data, right? And so what really is last right wins, though? Last right wins is talking about we're updating a shared value, and we're going to use whatever it is that we wrote into it last that is the correct value. So like when we had request C write that value into it, it's perfectly fine, right? That's what we expect. It's all well and it's good. And the problem is that this database of shared value and concurrency is the basis. This silly application I just showed you is the basis for all of the most popular architectures for scaling that you are going to go to conferences like Velocity and everybody is going to pitch you on what is at its core this. This is the basic thing which is happening underneath. We have a database or databases somewhere that are shared values. We're going to have a whole bunch of stateless services out in front of it. And boom, we can run into this problem, right? This goes by a variety of different names and patterns that happens for all of these. Serverless in the end, if you're doing serverless, which is stateful, and by stateful I just mean handling any state. So if you have a completely stateless, actual computer science definition of a function for functions as a service where it takes some input and every single time you give it that input, it will always give you the exact same output, you don't have this problem. But nobody really talks about, hey, I want to spend a bunch of money on Lambda functions in order to do that. It's, I'm going to put up some stuff on Lambda and it's going to write a bunch of stuff to a database. And there's going to be no coordination between these things. And if that database is a shared value between those requests, we're going to have this corruption. Stateless, this is my favorite one. If you follow me on Twitter, I will invariably, after reading something or hearing somebody's talk, put stateless in quotes up there because, yes, stateless is built around this. We have databases somewhere where the state actually lives. There's no less in it. If you're a bit older and more academic, you might call this a shared nothing architecture. These are all, in the end, names for patterns which apply the same thing. And they all, like I said, they all feature a database as a shared value. And they all have concurrent rights. And they all have data corruption baked into the core architecture, right? So what can we do, right? I wouldn't want to end with just the, well, I don't know, it's been awful hot in my room. Maybe I would just want to end it with the depressing part of, hey, look, we're probably not doing this right for the most part. But no, I mean, there are many options that we can do in order to try and avoid this. And in the end, it comes down to finding something where we're happy with the trade-offs that we get from changing at least one part of the data race recipe that we have for these basic things. Sometimes maybe we do more of these. But really, there is no correct answer, and anybody who ever gets up on a stage and tells you that there's one thing which is definitely going to do it is just lying or probably up there actually pitching their company's product or something, who knows. So I'm going to apologize to you in advance for this slide and when you look up at it. But one of these things, which you could certainly use to help solve this, is there are means within standard SQL relational databases which can help you deal with this. One of those is one which is very, very, very unpopular in the web space, and that's to use stored procedures. We could take this idea of increment database value, turn it into a stored procedure in the database where there will only be a single thing which is accessing that stored procedure at a time, and we will get the correct value every single time. We've changed the data race. The problem is that the trade-off there is not one that folks who are generally concerned about scaling a web application are interested in, because stored procedures are going to, in the end, make your thing go slower. It's a fascinating thing. Like, protecting your data from data corruption can often make your application go slower. You can also use transactions. Transactions could make, transactions would be used in order to have this so that we actually have isolation within the database when we do these things, right? If you want to get really fancy, you could use distributed transactions, right? But these come with their own set of trade-offs. Distributed transactions are generally even slower than what you would get with what you're doing just inside of a database. But you could also potentially scale them much better than you could scale a individual database where you're putting a lot of load on it by asking it to do a lot of work by executing what is potentially complicated logic in a stored procedure. Both of those really are examples of a broader thing in general, which is we need to synchronize data access, right? The actor model of computation is all about synchronizing access to values that would otherwise be shared. And if you have any familiarity with languages like Erlang or Elixir, you might have seen this. There's no way for multiple things to be accessing the same shared value. You have to communicate through some type of message passing mechanism for this. In the end, that's a synchronization thing, right? There will only be one writer. We've removed the multiple writers to this particular value. You could also do event sourcing, which just has a single writer. Where you're just writing out the changes that you want to make to something. You'd have to do a few other things along the way. And there's also an access pattern called CQRS, where we break apart our reads and writes from each other. And there's a whole bunch there where now, what I wrote is not necessarily what I'm going to read back, but there are trade-offs in all of these things. And again, there are links to all of this that will be in the GitHub repo, because any one of those things I already mentioned before we even get to these others could take up a whole talk. We could use consensus algorithms like Paxos or Raft in order to agree across multiple different things that we're scaling on what is the value of that value right now, and then to be able to update that in a fashion where we can do it. As Lena mentioned this morning, it's like, hey, oh look, there's a bunch of my talk here at the end of hers. We could use concurrency-friendly data structures in order to do this. Probably the type that most people have heard about are called CRDTs. These are data structures which are really designed to have multiple different things to be reading and writing from at one time and be able to come up with an agreed upon value for what a thing is as they start to come together. They're really core to a lot of eventual consistency type stuff, right? But an awful lot of these are built upon a change that we need to make in terms of how we're actually communicating changes to our data, right? Which is we need to communicate operations rather than values between different parts of a system, right? So we want to send increment 1, not change value to 2. If we change it to change value to 2, we're always going to be susceptible to interleavings, to concurrency problems, to that last write wins issue. All of these are going to happen. But if we communicate instead increment 1, which is what we really wanted to do, and then wherever that is responsible for being applied is then synchronizing access to that, we're never going to get this type of data corruption. It's not going to happen. But it's a matter of changing our patterns for how we communicate. That even this ends up potentially having trade-offs. How do you communicate operations if your thing is a customer's address, right? And you want to say, Alex here in the front here has moved from San Francisco to Los Angeles and I need to update this record, right? But somebody else is going in at the same time and had a thing of his apartment number was different because somebody else is doing something, and they come together. There is no simple operation which will put these things together, right? It's great for mathematical operations where we want to add 1. It doesn't matter what order we add 1 into anything, but there's still ordering issues that are there. So, there is no correct way to do any of these things. There's an awful lot that you can look into for ways that you can do it. The one thing that I would ask everybody to do is to potentially stop doing the pattern that we normally do. And there's one other that I want to talk about, one other, which is really the answer of, if this is really so bad, how come everything that we do is built on this? And if you look at almost every one of the early websites, and still an awful lot of websites today, there's a database on the back end, but it's not a shared value. It's really not in almost every situation. If you think about like a website like Twitter, if you go to Twitter, if I update my profile on Twitter, how many other people are updating my profile at the same time? Nobody. It's not a shared value in that particular case, even though it's in the database. And a large number of websites and a large number of applications are, even though there's a central data source somewhere, it's not acting as a shared value. It's the odds of like 2 customer service representatives at, say, Verizon that keeps messing up my bill repeatedly over and over and again for the last 6 months, going in and modifying my account at the same time and updating the same value in the database for like my account or something is really, really, really slim. So taking all of these trade-offs that might come by using distributed consensus or something else is just not worth it, right? It's the data handling equivalent in those cases of being like, hey, my website needs to handle like, accepting 10 new customers like every week or something. So I built myself this big, giant, fancy Kubernetes cluster in order to be able to scale this up and down on demand, right? Like, you might not need it. So just remember, that database existing there doesn't mean it's a shared value. You actually have to have things which are trying to write to it and update at the same time. That's really all I have for today. Again, there's links to an awful lot of stuff that are there. There's words, lack of sleep in the heat. There's the slides from today's talk. This is slides from when I gave this like 3 or 4 weeks ago in Columbia. There's also a copy of that. And hopefully this has been helpful and people find some stuff in the repo that they really want to dig into. And we have 7 minutes, so if anybody has questions, I can do those. Or you can come find me anytime today, including right after this, before 5 p.m. when the puck drops at the Bruins game. We can get my Bruins shirt on here for future video. There we go. Go Boston.
Thanks. Can you talk a little more about, you talked about CRDTs?
CRDTs.
Yeah, what are those in real life?
What are those in real life? So unfortunately, most of the literature that you're going to find on CRDTs are generally things that involve usually something which is like a counter, and it's a fairly simplified thing. Often in the case of something where like you need to do something where you have my phone might go offline, right? And I want to be able to communicate changed values that I did on my phone while I was offline back to some central service. And the idea for a CRDT is you have a data structure which has it has basically what's called, it's a merge function, which is built into this, right? And the merge function is how do I take multiple updates to this and decide what to do for them? And there is an algorithm for each data structure to decide that. There are CRDTs where the merge function is last write wins, right? That is still there, but there can be plenty of other possible strategies for how you go about this. Like, you'll find CRDTs for sets, right? For example, in the literature, and a big question there is what is the merge function if you and I are operating on a thing independently, and you say add 1 to the set, right? And I say remove 1 from the set, and we have no idea when each one of us did this, but they arrived at different times, right? How do we really decide, how do we decide how these things work? And that's a really simplified version, but in the end it is, most people usually say, is it conflict-free replicated? Yes, thank you, conflict-free replicated data types. There's one that somebody else, there's another one there that I often get tripped up on. But yeah, that's basically about it. And it's usually like, hey, there are operations that have to be able to commute for these in order to really work as a data structure. And they can be incredibly slow, and they often have to keep a ton of information around to really work. And they're a data structure where garbage collection is actually an issue just for the data structure. And I don't mean like garbage collection in the way that like I created an array on the JVM and eventually it needs to be freed, but there is potentially a huge amount of overhead for those.
Any more
Cool.
questions? Excellent. Thanks, everybody. Thank you, Sean, for the great talk.